We're back for more implicit differentiation. And I got you this meme. Get it? What are you trying to imply? Implicit. That deer's face. Away we go. Okay, so the example, all of the examples that we did the other day were pretty straightforward implicit differentiation problems because each term only had either an x or a y. So it was pretty straightforward. We took a derivative and we decided, are we going to do a dx dx or are we going to do a dy dx? In this problem, I want you to notice that we have a little jumbling of terms. It's a bit more complicated because this, when we take the derivative of this is an x term, right? I'm going to do a dx dx. When I take the derivative of this, it's a y term. I'm going to do a dy dx. This middle term, though, has both an x and a y. This is not a problem. We just have to be careful about what we're doing. Remember, that's a product, right? We take the derivative of a product, we use the product rule. At the point when we're taking the derivative of something, that's when we tack on our dy dx or our dx dx. Remember, it's kind of like a chain rule chunk. So the question as to which one we're going to tack on is going to be determined by what we're taking the derivative of. So I'm going to break that into two pieces and do a product. When I take the derivative of the 18x, I'm going to do a dx dx. When I do the derivative of the y squared, I'm going to do a dy dx. Okay? But it's not until the moment that you take the derivative of something that you tack on the dx dx or the dy dx. I'll show you what I mean. Okay, so let's take the derivative of 10x to the fourth. That's going to be 40x cubed dx dx, right? Okay. Now, I have minus, and I'm going to be real careful here. I have minus, and there's a product. So I'm going to type minus, write minus, and then I'm going to open a bracket because I know when I do a product, I'm going to end up with a sum in here, and I got to make sure I distribute this negative. Okay. So I'm going to look at this as two pieces, an 18x and a y squared. So I'm going to do 18x times the derivative of y squared, or 2y dy dx, okay, plus y squared times the derivative of 18x, which is 18 dx dx. Now again, I cannot stress enough that I did not take the derivative. I did not do the dy dx or the dx dx until the moment I took the derivative of that piece. When I took the derivative of y squared to 2y, I added the dy dx. When I took the derivative of 18x to 18, that's when the dx dx came in, and not a moment sooner. Okay. Now I need the derivative of 10y cubed, so that's 30y squared, again, dy dx, and then equal to 0, because the derivative of 48 is just a 0, it's a constant. Now again, notice the fact that we have a product here made our algebra a little bit more complicated, but it's nothing we can't handle. Okay, so let's see, I have a dx dx here and a dx dx here that I don't really care about. I have two dy dx terms. So let me rewrite this so that we can solve for dy dx. So I have a 40x cubed. I have a minus 36xy dy dx. I have a minus 18y squared. And then I have a plus 30y squared dy dx. Now, as I said before, what we want to do algebraically is find our terms that have dy dx in them. This guy and this guy. I'm going to leave them on one side, and I'm going to take the other ones to the other side. So I'm going to have a negative 36xy dy dx plus 30y squared dy dx on the left. And I'm going to take this 40x cubed and this minus 18y squared, take them to the other side. So 18y squared minus 40x cubed. Okay, now again, over here, I'm now able to factor out my dy dx. So the algebra of this gets a little more interesting the more terms you have, but it doesn't change the general process. I'm always going to do my derivative, tacking on my dy dx or my dx dx where necessary. Everything that has a dy dx stays to the left. Everything that doesn't goes to the right. Factor it out, and then you divide, and you're all set. Okay, so my final answer here is going to be dy dx 18y squared minus 40x cubed, all divided by negative 36xy plus 30y squared. I'm guessing there's at least one simplification there, right? At least we can divide by 2. I'm not doing it. I'm leaving it right like that. Okay. Another example. So if we take a look at this one, again, we have x's and y's jumbled. Might be able to get at y if you worked really hard. Why bother when I could just use implicit differentiation? Remember, it's never wrong to use implicit. It might be extra, but it's not wrong. Okay, so I'm going to take the derivative of this side, and notice when I take the derivative here, I've got a little chain rule action. Okay. The dy dx and the dx dx aren't going to show up until I'm doing the chain rule, right? Because until the moment I take the derivative of this x, I'm not tacking on a dx dx. And until the moment I take the derivative of this 2y, I'm not tacking on my dy dx. I'm going to have them show up again on the other side of the equation, and I'll deal with that when it comes. All right, so let's do the chain rule over here. I have 2 cloud to the first, and then I'm going to do my chain rule piece. Again, this is where my dy dx is going to pop out. So I'm going to take this and do the derivative. So again, it's a quantity, so I'm going to, all right, derivative of x is 1 dx dx, and the derivative of 2y is 2 dy dx. Okay. On the other side, and the derivative of x, which is 1 dx dx, the derivative of y, which is 1 dy dx, and the derivative of 1, which is 0. All right, so again, we have a little bit of algebra to be done, but if you go back through here, there's a dx dx here that we don't care about. There's a dx dx here that we don't care about, but be careful, those are 1s, they're not 0s, right? This is an actual 0 that I don't care about at all. All right, so I have 2 times x minus 2y, and I need to distribute it to these two things. Now, why do I need to do that? Because one of these terms is staying on the left, one of these terms is going to the right. So I have 2 times this quantity times 1, and then minus 2 times this quantity times 2 dy dx. So I'm going to say 4 x minus 2y dy dx. Over here I have a 1 and a plus dy dx. So again, I have 2 terms, one here and one here, that have dy dx in them. Those I want on the left, this guy and this guy that don't have dy dx's in them, I'm going to bring to the right. So if it's okay with you, I'm going to do 2 algebra steps in 1. I'm going to switch my terms to where they need to be. So I'm going to bring this dy dx term over here, and I'm going to bring this non-dy dx term over here, but I'm also going to write it with my dy dx factored out to save myself a little bit of writing. So on this side, when I factor out my dy dx, I'll be left with a negative 4 x minus 2y and a minus 1, because I brought over a 1 dy dx. On the other side, I still have my 1, and I'll bring this over, so it will be minus 2 x minus 2y. And again, the last step is the same every time. To get my dy dx, I'm just going to divide through by this. So I'm going to 1 minus 2x minus 2y all over negative 4x minus 2y minus 1. I'm done. Do you love implicit? It's so fun. Okay. Again, people tend to get a little bit lost in these more complicated ones, not sure when to write the dy dx. So they either forget to write it, or they write it too soon, or they write it more than once. cannot stress enough that it is not until the instant you physically take the derivative of the thing that you tack on the dy dx. Again, notice our dy dx did not show up here until we were inside of doing the chain rule. I didn't take the derivative of this until I chain rolled, and it's not until you take the derivative of it that you tack on the dy dx. Okay. All right. This is another one. The algebra, this one looks like it's going to get fun. But again, notice I have a y inside of a cosine. So I'm going to have a dy dx show up here, but it's not going to be until I take the derivative of the y cubed. And over here I have a product. So I'm going to have another dy dx show up here, but it's not going to be until I take the derivative of this y. All right, so let's do the derivative of the left and the derivative of the right. The derivative of the cosine of something is negative sine of that something times product rule. So x squared, derivative of y cubed is 3y squared dy dx, plus y cubed, derivative of x squared is 2x dx dx. We'll cross it out right now. On the other side, I have a product. So y times the derivative of sine x, which is cosine x, dx dx, which is just 1, plus sine x times 1 dy dx. So I've got a dy dx here, and I've got one here. So again, because I had a chain rule here, I've got this that needs distributed. So this is a real heck of a lot of fun. So I have a negative 3x squared y squared sine of x squared y cubed dy dx minus 2xy cubed sine x squared y cubed equals y cosine x plus sine x, always, sine x dy dx. So I've got a dy dx term here and a dy dx term here. So on the left, I've got this whole mess. I'm going to factor a dy dx out. Negative 3x squared y squared, the sine of x squared y cubed. And when I bring this over, I'll have a negative sine x. On the other side, I've got my y cosine x plus 2x y cubed sine x squared y cubed, because I'm bringing this chunk over to the other side. And again, I don't care how complicated the algebra gets, finish it out the same way every time. I think the most annoying part of all of this is how much, I'm just making sure I didn't make it a little, I don't want to make like a typo here. I don't think I did. It's how much writing you have to do. I think that the most likely thing that would happen to me here is that I would copy something wrong. Okay, so again, I have the right side of my equation and I'm dividing by this quantity that's left over once dy dx goes out. I know it's a lot of writing, but please be careful and don't skip steps of algebra that's going to cause you to make a mistake. I know you don't like to write as much. Everyone's like, oh, lead conservationist. You guys try to do 20 steps of algebra in your head. And if you can do that, great, good for you. I can't. So I know I show an excessive amount of work. If you can do 2 steps or 3 steps at a time in your head, go for it. But please do be careful. Wardrobe change. Okay, the last thing we need to talk about in this section is taking higher order derivatives when you are doing a derivative implicitly. And there's only one little kind of thing that pops up for us. So let's take this example that we've already done the first derivative of. So if you remember earlier, we took the first derivative of this implicitly. So 2x cubed became 6x squared, dx dx, just a 1, minus 3y squared becomes 6y dy dx. And then my 8 turns into a 0. We solve for dy dx, and we get x squared over y. So we did this earlier. Okay. So if what I want is a second derivative, then we know that we need to take the derivative of the derivative. But notice here that when we take the derivative of this, it's going to be a quotient rule, but also it's an implicitly defined function. So when I do the second derivative, when I take the dy dx of my derivative, I'm going to have dy dx's popping out again. So let me show you what I mean. So if I want to take the derivative of dy dx equals x squared over y, I can easily do that. I don't have to worry about any of that old parametric stuff because I'm still taking the derivative of y with respect to x, as evidenced by my dx dx's and my dy dx's, right? But what I'm going to do here is I'm going to say, okay, let's do my derivative quotient rule. So denominator, derivative of numerator, dx dx, minus my numerator, derivative of my denominator, which is just 1 dy dx, all over my denominator squared. So you might think like, yes, Miss Britton, why are we talking about this? Well, we're talking about it for one reason and one reason only, because you're not done yet. So if I simplify this, I have 2xy here. I have y squared down here. Over here, I have x squared, and I have this dy dx hanging out. I can't leave my answer with the dy dx. You can't do that. But the great news is, we have this little trick in math that says that as long as two things are equivalent, you can swap them out for one another. And I just happen to know what dy dx is. Dy dx is x squared over y. So all I really have to do here is take this dy dx to be done and swap it out with this x squared over y. Just in other words, replace any dy dx's that pop up with what you know dy dx to be, so that your answer given to you defined implicitly, you're giving an answer, a second derivative, also defined implicitly. The general rule that you want to follow is however they give you your equation, that's how you want to give it back. So if they give you an implicitly defined function, it's fine to give it back. If they give you an explicitly defined function, you want your answer to be explicitly defined as well, just as a general rule. So here they've given us an answer, or they've given us a problem in terms of x and y. We want to return an answer in terms of x and y. We don't want to have anything else kicking around in there. It's not considered done until we've done that. Until we've done that like little substitution. Okay, let's do another example like this. Oh, baby. Okay, so we have the sine of y plus y cubed equals x minus x cubed. So let's take our first derivative. The derivative of sine is cosine y, and then a dy dx, plus 3y squared, and dy dx again, equals, I've got a 0 minus a 3x squared dx dx. So before I do the derivative again, I'm going to do some simplifying because, of course, we don't want to make a mess. So let's get an expression for dy dx. We're going to need it anyway. Don't make the mistake of going straight from this and being like, oh, let me just take the derivative of this and I'll use a product rule on this and this will become the second derivative, and then try to algebraically solve for the second derivative. You're begging for a mess. Begging. But I suppose if messes are what you like, what you like. Okay, so we're going to solve for dy dx, right? So I got cosine of y plus 3y squared over here. Ooh, nice choice, okay. And a negative 3x squared. So my derivative, and so often do they come out to be quotients. So often. Just because of the nature of how the algebra comes out. There's my first derivative. So my second derivative is going to be a quotient rule. So let's go. Cosine of y plus 3y squared times the derivative of my numerator, which is negative 6x dx dx, minus my numerator times the derivative of my denominator. So negative sine y dy dx minus 6y, or that's a plus, sorry, plus 6y, again, dy dx. All over the denominator squared. Now again, come up in here. That's a 1, I don't care about it. We could do a little bit here to simplify in this numerator. I'm going to erase above so that I can write it above. I just erased what dy dx was. It's okay, I can remember. Okay. So I don't know why, but I like to take this negative 6x out front, and then I have cosine y plus 3y squared. And then here I've got a plus 3x squared. And what I'm going to do here is I'm going to factor this dy dx out so I only have to write it once, just to make my life easier. Negative sine y plus 6y. And then I need to put my dy dx in here. So dy dx was negative 3x squared over cosine y plus 3y squared. Nope. There we go. So again, I had a first derivative we take the derivative of it using the quotient rule. And again, notice every time I take the derivative of something, I'm tacking on either a dy dx or a dx dx. And in the end, because I'm doing my second derivative, I just have to replace all the dy dx's with what I know dy dx to be. And in this case, I just algebraically factored the dy dx out, so I wouldn't have to write it twice. Oh, I just keep doing that. Okay, so let me know what questions you have on this second layer of implicit, and we'll talk about it soon. Have a good one. Well, you don't want to miss an answer point because you made a silly algebra mistake.